how they were discovered, then what are these different classes of insecticides under this category, and eventually it will end on the mode of action. The synthetic carbamide insecticides are not a product of accidental findings, unlike with organophosphorus insecticides, wherein its insecticidal property was just observed accidentally. The first objective in the synthesis of products during the World War II was actually to make a chemical warfare. And one big company in Germany, the Farben Industry Aktiengesellschaft, was commissioned to produce nerve poison or nerve gases. In the case of carbamates, it is a kind of product development for insecticides, wherein its synthesis was based from the naturally occurring natural products in Physostigma venenosum, and this is a leguminous plant, and the beans contain the principal alkaloid that makes it insecticidal. And physostigmin is an alkaloid. Now, I think you don't know what alkaloid is. It is a natural product present in many organisms, be it in plants, animals, or even a microorganism. What you are going to remember with physostigmin, it is a compound with the presence of nitrogen. Now, physostigmin as a chemical compound known to be an inhibitor of cholinesterase. Cholinesterase is an enzyme that would act upon acetylcholine to break this acetylcholine into acetic acid and choline. Acetic acid and choline, which is an alcohol, is very important in the biosynthesis of acetylcholine. You know that acetylcholine is a neurotransmitter. It would transmit it is a chemical that is needed in the transmission of impulses from one nerve cell to the next, and the transmission occur in the synapse. This is just a review of your insect physiology, especially on nervous system. You can still remember the structure of its nerve cell. One cell will be connected with each other, and there is a junction in between, which is called a synapse. In the synapse, this is where one impulse will be transmitted to the next, but it will be aided with acetylcholine, which is a compound needed for the transmission of impulses to proceed. Now, as a compound, physostigmin is also an anticholinesterase. If it's an anticholinesterase, it would inhibit the availability of cholinesterase, an enzyme, as I've said, necessary in the breaking down of acetylcholine into acetic acid and choline. The development of carbamates came into being after the production of organophosphorus insecticide. We know that organophosphorus insecticides are potent nerve poison. It is highly toxic to mammals and other animals, but their availability during that time has no competition at all. And with the problem associated with the use of organophosphorus insecticide, this now led to the development of carbamate insecticides right after the production of organophosphorus insecticides in the 1950s. I will give you the picture of Physostigma where the alkaloid is being extracted. This is a tropical plant that is a native of Africa, and it is highly poisonous to human beings. The name itself, it is derived from the first part of the scientific name, from a curious beak-like appendage at the end of the stigma, like in the flowers, and that's why it bears the scientific name Physostigma venenosum. Uh, how how does one discover its poisonous substances? During the olden times, there is no lawyers available yet. People would use means to discover who are those individuals committing crime. And one way of evaluating it, especially in Africa, there are different tribes. They have this community where it is headed by a shaman, I mean by a priest or shaman, this witch doctor, and they are the one involved in investigating any crime that will be committed in the community. It's very hard to hear hearsays without a validation, and hearsays usually what would reach in the last receiver would be now not the same version. Most likely there will be minus and plus information that will be given. In the case of Calabar beans that is used to evaluate and identifying the culprits, the shaman or the witch doctor would prepare a potion, a potion. This is a drink, actually, laced already with the extract of the beans. And since it is a nerve poison, the one that is committing a crime would feel nervous, and in doing so, there will be an elevated blood pressure with fast heartbeat, and these conditions would lead to faster distribution of the toxin in the body of the individual. It was practiced long before, and there are still some tribe that is doing this time, and the intoxication portrayed by those individuals who drank the potion would be the basis for indicting a person or not. So what is this ezerine or physostigmine in terms of structure looks like? It is, and as a basis in the development of carbamate insecticides, we know that carbamate is a derivative of carbamic acid, and this is the one that you would see. Carbamic acid is actually the monoamide of carbon dioxide, which is a highly unstable compound, and its instability would lead to decomposition, giving carbon dioxide and ammonia as products. Now, this carbamic acid may be stabilized by forming salts such as the ammonium carbamate, or substituting part of the molecule by alkyl or aryl esters. This is the basic structure of carbamate insecticides. You have to comply this structure. You can only change it in the R1, R2, and in R1, R2, this can be substituted with either hydrogen, methyl, ethyl, propyl, or other short-chain alkyls, or the aliphatic hydrocarbons. Now, R3 is substituted by phenol. This is an aromatic kind of or naphthalene. This is a bibenzene. This is a fusion of two benzene rings. or other cyclic hydrocarbon rings. This discovery of carbamide pesticides started way back in the mid to late 1940s. The synthesis is based on the carbamic acid, which is based from physostigmine, which is potent neurotoxin, and the first ever carbamate synthesized was not actually used as we have this time, which is a broad spectrum insecticide in many cases, but this time the development was geared towards new insect repellents, and the effort was successful, that a certain insecticide was produced. The development of carbamide insecticides is a need-based driven kind of development, and with the advent of the organophosphorus insecticides during the World War II, its use was expanded not only as a control for insects that are effective vectors of many pathogenic organisms. During the World War I, the problem was on malaria for the combatants in the forest, and also the incident of typhus, which is caused by bacteria, and it is carried by one of the insects like houseflies. It is a common contaminant, and it can cause diarrhea and other manifestations, and the need of such insecticides to ward off these vectors was so necessary. Now, the development of carbamide insecticide was initiated by Hans Geisen, who is a Swiss, and along with the collaboration of Dr. Robert Metcalf in the US, their collaborative efforts led to the discovery of aryl methyl carbamates, and they were able to come up with a product called Carbaryl, and then this is produced commercially by Union Carbide. By the way, Robert Metcalf is a renowned entomologist in the US. His book on entomology, on basic entomology or giant entomology, was used until now. I am one of the users during my studies when I enrolled in plant protection as a specialization in agriculture. His book until now is being used as one of the textbooks. Actually, he has lots of experiences in dealing insects. Thus, his work with Hans Geisen produced a very successful product to control our pests. The development of carbamates, like any other insecticides, can produce various products, and for carbamates, all these products produced synthetically can be classified into naphthyl, phenyl, heterocyclic, dimethyl derivatives, and oximes. We are going to discuss this one by one. For naphthyl, what is important here is the replacement of one hydrogen associated with nitrogen with methyl group. So here you have to look at the structure of carbaryl. This is the part that is very important in substitution. This is now the R1 and R2. Then you have the R, and this one you can attach the heterocyclic rings. Now for carbaryl or for naphthyl kind of carbamates, the name is derived from the naphthyl substitution in R3. And naphthyl is actually two benzene rings fused together. This one. Here, in carbaryl, the substitution, as I've said, is a naphthyl, and then you have a substitution in R1 and R2. Now, in one of the substitution is the nitrogen, and we know that nitrogen is a trivalent, and it has to have 3 bonds here. If there is a substitution in R1 or it could be an R2, what is left, there should be another bonds that would be produced. In this case, it's only the hydrogen bond. And this one, this is the carboxylic part of the molecule that is now actually important when we go into mode of action that would play a very important role in attaching itself to the stereotic site of the enzyme. Now, carbaryl is one of the first products actually produced in carbamate groups. It was introduced in the market in 1956 under the trade name of 7. 7, I think, is a dopant, or I forgot the company that produced it. Anyway, or union carbide. Since this time there are already a number of formulators buying the patent of this compound from those who were able to synthesize it. Okay, the next group are the phenyl carbamates. You have to look at also the substitution. In the first part, the substitution is in here, but the first part was a naphthyl substitution. This time it's a phenyl ring substitution. Now here in this ring, you can also play around in the different carbons there by attaching many functional moieties to increase the efficacy of a particular carbamate or even increase its persistence. This is still the same, since this is the basis in the production of carbamates. Now, phenyl carbamates like OPs, it will interact in the cholinesterase, which is an enzyme, and this is the part which is the esterotic part of the molecule that would bind now in the esterotic part of the cholinesterase. Okay. Now, the interaction this time would be through van der Waals forces at the esterotic site of the enzyme, and this is also the esterotic part of the molecule, and there is a good there's a good fit in when you look at the structure of the molecule, and where in the enzyme they have to be incorporated, or they have to attach itself to which part of the molecule in the enzyme. We have here 4 examples of phenyl carbamate insecticides. We have isoprocarb, a same structure as before with carbaryl, or the other one, but then this is actually a phenyl group. No, here this is the part where you can consider it as phenyl. This is if you're before the synthesis, you have here a ring with an OH here. Look. So isoprocarb, propoxor, phenobucarb, and methiocarb, these are all insecticides that are classified under phenyl carbamate insecticides. It's easy for us to remember based on the name itself. If it is naphthyl, then if it is phenyl, then it bears some phenolic ring as part of the molecule, and you can also do a lot of substitution within the phenyl ring, such as here. You have here a dimethyl, and this is a methoxy part here. Then you have here an isopropyl here part, and here you have dimethyl plus sulfomethyl part as functional moieties in the phenyl ring. Let's proceed to the next group, which is the heterocyclic dimethyl derivatives. And with this group of carbamates, it is a heterocyclic compound which has atoms of at least 2 different elements as members of its ring. No? Like for example, this one here, you have nitrogen, then you have one ring here with nitrogen, you have 2 rings here, you have a benzene ring, and then a furan, a double-banded furan. But if it is a simple furan, then you'll have five rings here, but part of which is already have a substitution of sulfur. Here are some of the heterocyclic dimethyl carbamates, and these 4 are more popular this time, and the most popular of which is actually the carbofuran. This is a popular insecticide used by many of our farmers, especially those in corn production. It is the same compound that is being used this is the compound that farmers would put on the whorls to control stem borer, and it is also used as a soil fumigant, apart from soil fumigant to control insect pests found in the soil. Carbosulfan as well is also popular, and with this structure here, carbosulfan is more toxic because of the presence of additional functional moiety here, which is sulfur. For benfuracarb, you have the same part here and also this one, but it's the substitution in R. Let me see, this is R1, R2. No, it's an R2 that makes the molecule appears a little bit more complex. Much more with indoxacarb, you have here more of the aromatic rings attached to the basic carbamic acid. Now, if you are just keen in looking at the structure, in indoxacarb, there is halogenation there. Halogenation, or it's the incorporation of halogen, and we know that there are 4 halogens that can be used in many of the synthesis of chemical compounds. We have chlorine, we have fluorine, we have bromine and iodine. Normally, for insecticides, only 3 halogens are used. It's the chlorine, fluorine, and bromine, and we will encounter this halogenated insecticides as we will discuss lesson 4.4, that is on pyrethroids. This substitution here with halogens make this insecticide more persistent. Any compound that bears halogen in it, it would contribute to its longer shelf life, and they are more stable, they cannot be easily degraded. This makes them more persistent in the environment. But while these are persistent, there are also other parts of the molecule that would contribute to its persistent, but not with the previous insecticides we were discussing before on chlorinated hydrocarbons. since the structure here is not that tight, I mean the functional moieties are not tightly bound. They are still subject to a chemical attack like this one here. These are highly nucleophilic portion of the molecule, and they can interact with other compounds easily, and the chemical reaction could take place in the same manner here. No? But this one, you have to look at the presence of oxygen. Oxygen is a good nucleophilic element. Okay. Now the last group of carbamates are the oximes. These are derivatives of aliphatic oximes. Aliphatic oximes, by the way, comes from the word, from this aliphatic, these are alkyl hydrocarbons with oxygen in it. And its derivative is of this compound rather than esters. The other group of carbamates are esters in terms of chemical classification, but for oximes, they are either aldehyde or ketones, and they are collectively known as methyl carbamoyl oximes. Why methyl carbamoyl oximes? One of the functional moieties is a methyl part of the molecule. And then if you look at where nitrogen is being attached to, it is directly attached to the oxygen and the double band nitrogen in R3. If you go back to the structure of carbamic acid and also the basic structure in the synthesis of carbamates, you have three substitutions that you can play around. It is in R1, R2, and R3, and you have to bear in mind that R1 and R2 are alkyl substitutions, either a hydrogen or methyl, ethyl, and propyl, or other short-chain fatty acids. No, not fatty acids, short-chain alkyl group. Okay. Now, we have here examples of oxime carbamates. We have aldicarb, which is also still popular these days, but the most popular of which is methylamine. It is marketed as lanate by DuPont, yeah, and it is one of the insecticides DuPont produced that makes this company very rich. And even if it was produced in the early 60s, but then its use as an insecticide remains now it is one of the highly saleable carbamates in the market. This one. And methylamine, during the synthesis, it can occur into isomers. You have to look at the position of the substitutions here, and yeah, this one. The other is why you can have this one. It can easily twist in this part of the molecule when it is subject to the reactions. Now another one is dimethyl carbamates. In dimethyl carbamates, you have two methyl functional moieties attached to N, like this here and here or here. So dimethyl meaning two methyl attached to the N part. We have done discussing on the different kinds of carbamates based on their structure, and you could also see how each of these carbamates behaves if the different substitutions. The substitutions of any compound would determine its physical and chemical properties. Going to the mode of action of carbamates, we know that carbamates are potent cholinesterase inhibitors, and they share the same mode of action as that with organophosphorus insecticides. The difference of which is actually in terms of the aging process and also the strong binding of this carbamic acid into the stereotic site of the enzyme. Now, the process in terms of production of the toxic effect of carbamates is similar to that of organophosphorus insecticide. The difference only here is that in carbamates, you have an stereotic site of the molecule that will now attach to the stereotic site of the enzyme. During this process, there will be carbamylation of the acetylcholinesterase at the neuronal synapses and neuromuscular junctions. This is the site of action where carbamates would take place. The mode of action, don't be confused with the site of action and the mode of action. The site of action is the place. Mode of action is the process when an insect is intoxicated. The mode of action is the process. The site of action is the location. Now, for carbamates, what is interesting here is that during the process of carbamylation, there is this reversible reaction since the binding is not that strong as compared with phosphorylation. And in phosphorylation, the dissociation in the enzyme is takes longer than the carbamates. During the carbamylation process of the enzyme and phosphorylation of the enzyme in the case of organophosphorus insecticide, there will be a product that is produced that is now the carbamylated cholinesterase and carbamylated and phosphorylated cholinesterase. Under normal conditions, since one of the the main chemicals involved in the transmission of impulses is acetylcholine, which has almost the same chemical, what you call this? They have this structure that easily fits into the acetylcholinesterase, which is the enzyme needed in the degradation of acetylcholine into acetic acid and choline. So here, when there is the presence of carbamates or organophosphorus insecticides, there will be no binding of acetylcholine into the acetylcholinesterase. What happened is there is a competition now. Instead of acetylcholine that will be bound into the acetylcholinesterase, it is now the carbamate in the stereotic site of the acetylcholinesterase. Now, if you look at the structure of carbamate, it is the hydrophilic part that will now attach to the stereotic site, and this is the one that is subject to deesterification, and it is now the dissociation again of this complex, and the process would continue in a spontaneous manner. And what would happen, there will be no more acetyl, there will be a production of more of this carbamylated enzyme, that when these enzymes would no longer be available to And since acetylcholine is involved in the transmission of impulses, there is a firing state of the transmission of these impulses. And what would happen? The insect would don't have any resting stage. So eventually, these insects or even human beings or any non-target organisms coming in contact with these compounds would get intoxicated. If you are going to compare carbamates vis-a-vis organophosphorus insecticide, carbamates is less toxic compared with organophosphorus insecticide. Why? The reason for this is that carbamates can undergo reversible type of reaction since the dissociation with the enzyme is faster compared with the OP, but its presence is still important since there will be no more enzyme that would act on the acetylcholine. And that's how you're going to explain the intoxication process when one is exposed to either carbamates or organophosphorus insecticide. So that ends our discussion on carbamates. And I want to ask anybody of you that can summarize what we have learned in lesson 4.3 that is on carbamates. Anybody? Okay, others left on the meeting, maybe they have problems of connectivity. How about the others? I have to wait for questions and comments, and I have to wait for your questions before we will proceed to the next topic that is on pyrethroids. Any question? Some more are coming, actually more are joining in this group. Okay. So anybody of you that can summarize, that can recapitulate on carbamate insecticides? Do you have anybody? Kinsaman, who wants to volunteer? Si Dave kaya? Dave, can you summarize? Are you there? If not, then she's Sherilyn. Sherilyn, can you summarize? Like what we did in our previous lectures, that I asked anybody of you to summarize what we have discussed in 45 minutes, actually. So wala. I don't know if I was discussing too fast or you did not understand my lecture, and your comments, your suggestion would be the basis if I will continue or not. Asaman, who wants to answer? Si Jared? Jared, can you summarize? Jared?
Ma'am.
Can you summarize of the things we learned in carbamates? And you can start with the part of the lecture, then it will be continued with other students or other participants. Wala?
Oh, naputol-putol man gunong signal, ma'am.
Putol-putol lagi. So, how about the others who do not have problem with the signal? Kinsa man ni? Si Jennifer. Jen? Can you summarize, Jen? We barely have 4 minutes for this. Then I will proceed to my lecture on pyrethroids. Maybe they have also problem. They cannot hear me clearly. So Jennifer, Jen,
One of the character, ma'am.
yeah, kindly give the summary of what we have discussed on carbamates.
One of the characteristics of carbamates katong synthetic derivative siya sa physostigmine,
Tignin.
which
Okay,
is
very good.
part ato niya kay katong leguminous katong calabarbin.
Yes.
Then ang carbamates is anti-cholinesterase.
Erase. Oh,
So
good. Good.
na-develop ni siya sa katong in the year 1950
Uh-huh.
after sa phosphate. Then
Yeah.
kuan natin classifications na belong
Mm-hmm.
dito ang naptel,
Mm-hmm.
kalimut ko sa uban ng
Yeah.
oxime.
Oxime, yeah. Very good.
Then ang mode of action ni kanang
Uh-huh.
kanang pareha-parehas yan sa
Phosphorus.
organophosphate.
Okay, well said, uh, Jen. You capture it in few sentences, and that's the essence of carbamate insecticides. I hope some of you listened to the answer of Jennifer. This is one of the questions that would be given during the final exam. In the final exam, if it is an essay, I don't want to have a very long answer, short but concise. Short and concise, it means that it should be short enough but complete in its essence. Okay. Thank you, Jen. How about the others? Do you agree with what Jen is explained?
Yes, ma'am.
Okay, good. Do you allow me to proceed to the next topic?
Okay, ma'am.
Okay,
Yes,
good.
ma'am.
Okay, thank you. By the way, the carbamate topic was already uploaded in the e-learning. I will upload the pyrethroids in the evening. Okay, I'm just so busy. And I was not able to do it at home. The connectivity was so weak over the weekend. Okay. Okay, so I have to get the other topic. We have 1 hour to go, and we can finish it in less than an hour actually. Okay. Is it clear on your side? We are now in Module 4, Lesson 4.4 on pyrethroids. Is it clear? Can all of you see it? Okay. Now, before I'll proceed with our lecture, can you still remember one of the items we discussed on insecticide research and development, where pyrethroids was mentioned? Can you still remember it? It was given 2 weeks ago in Module 3, in which part of our lecture where pyrethroids had been mentioned. It was the time when we were discussing before the advent of synthetic insecticides. I remember pa mo? It is actually on the botanicals. Just to have a short review, in that module, we were discussing on botanical insecticides that includes nicotinoids, nicotinoids, the nicotine. Then we have the rotinoids from dairies and even from syncamas, and then pyrethroids from pyrethroids is actually the synthetic form of pyrethrines or pyrethrin, which we can extract from two species of chrysanthemum. Now let's go to the characteristics of these pyrethroids. As we know, this is just a review actually here, where pyrethroids are synthetic organic derivatives of the natural pyrethrin extracted from two species of chrysanthemum, and the pyrethrum, which is a more purified product after extraction. Excuse me for a while. Pwesta ka ng mga tong kang kuan, signature ni Bert para ma-recall tong message ko. Okay. Sorry, I just instructed one of my staff here. Okay. Now, pyrethrum, as I've said, it is one of the compounds that is present in pyrethrin, and it contains a mixture of 6 esters, which are a combination of 3 different alcohols and 2 different acids. The alcohols are pyrethroalone, cenerolone, and jasmolone. If strictly speaking, in terms of classification of compounds in chemistry, if we said alcohol, it should end with all, like ethanol, propanol, butanol. But in this case, it ends with on. That means that this is also a ketone. Why we use alcohol instead of the ketone as its name, instead of pyrethroal or cinerol and jasmol as alcohol, but what is being used here is the suffix ONA, and ONA is the suffix used for ketones. And you will know the answer when I will show you the structure of these 3 alcohols along with the 2 different acids present in pyrethrum. Okay, here they are. This is the structure of pyrethroalone. If you are going to see which part of the molecule that are, moment, nag-jump siya. Which part of the molecule differs here. For example, pyrethroalone, the difference is in this alkyl chain. Here, there is only 1 double bond. Here, there are 2 double bonds. Here, it has only 1 double bond, but there is a methyl after the first double bond in the case of pyrethroalone, and this one here, there are 2 double bonds here. Now, why the ketone suffix is being used? Because of this part of the molecule, this oxygen bearing A double bond. And any structure with this one is a ketone, by the way. Now, for the acid part, you have here a chrysanthemic acid, which is only a monocarboxylic acid, mono meaning only 1. In contrast with pyruvic acid, it contains 2 carboxylic acid here and this one here. That's why the pyruvic acid is a carboxylic acid monomethyl ester. Monomethyl meaning only 1 methyl part, and this one monomethyl, 1 methyl here, but there are 2 carboxylic acids. Here, this is simpler in terms of its structure. Now, this chrysanthemic acid can bind with pyrethroalone, cenerolone, or jasmolone in the process of esterification. this pyruvic acid would also work in similar manner to bind with pyrethroline, cinerolone, and jasmolone. And the process of sterification using these three alcohols and two acids would produce six kind of different esters. You have here the different esters being enumerated depending on the substitution in R1 and R2 and the type of um, acids used. Now, these six esters, which are actually natural products um, within the pyrethrum uh, extract, uh, all of them are quite unstable. They are susceptible to light, and then they are photolabile, and then they're also sensitive to moisture as well as to air. However, these six pyrethrum esters possess knockdown properties in insects. If we say knockdown, it can affect the insects readily and immediately. The insects affected will becomes jittery, and eventually they will just drop off on the ground where they are treated, and then but these knocked down insects have the ability to recover, especially if the the dose where they are exposed to is at the sublethal dosage. If these insects receive sublethal dose, while they are affected in terms of being knocked down easily, but this insect would recover eventually. The unstable properties of the six esters are being solved by looking at a part of the molecule where you can have a lot of substitutions, answering the problem of uh, photolabile and easily degraded upon exposure to moisture and air. And the new generation or the new synthetic products, since these are the natural products you can have in your extract from the two species of chrysanthemum, it is here that the organic chemist would play around to solve such kind of problems. Okay, the discovery of pyrethroids began in 1945 by Laforge and Barthel, where they discovered the insecticide property of pyrethrins, the natural products, and it is the basis when other chemists follow his footstep in the process of making new synthetic products of pyrethroids. The structure was elucidated by Godin et al., meaning Godin and his team in 1966. What does elucidated means? This is the kind of analysis by organic chemists how they can draw such kind the chemical structure of that particular compounds. We have equipment used in elucidating the structure. It is just based on the fragmentation pattern or on the different peaks exhibited in many of these highly sophisticated gadgets like the NMR or GCMS, MS, etc., etc. Now, the insecticidal property of which was reviewed by Japanese entomologists and with these entomologists in the 70s, and after that, working with chemists and entomologists together, then they were able to develop increasing the efficacy of the naturally based insecticidal compounds pyrethrum, and also making the new product being more stable after exposure to light, moisture, and even air. And it is also in the substitution in the molecule that one can have more persistent kind of pyrethroids. Normally, pyrethroids are highly degradable. They are non-persistent. Their activity is only short-lived. They can only stay on the treated surface for a few days. But with the new generation insecticides, we can have even longer. Now, you have to take a look of these different different pyrethroids produced in the early days, like the first generation insecticide and the second generation insecticides, wherein in this group of insecticides it can even be further classified into type 1 and type 2 depending on the substitution. I will discuss more of this after we discuss the different groups of pyrethroids, starting from the first generation pyrethroids. The first product came out in the market in 1949, followed by second generation pyrethroids in 1965 up to 1973. Then the third generation pyrethroids appear also during this period, in the later part of producing the second generation pyrethroids. And the ones available in the market this time are the third generation pyrethroids and the fourth generation pyrethroids. What are these different pyrethroids belonging to different categories? Let's start with the first generation pyrethroids. The first product that appeared in the market was alitrine. It appeared in 1949. Here, the molecule appears complex. With its complexity, it requires 22 chemical reactions in order to arrive this particular compound. In the synthesis, it's not as simple as you think. We're going to make the raw materials first, and then it has to be cooked in the laboratory. I will just use the process of cooking. Essentially, when you go into synthesis, you are literally cooking these compounds either under extremely high temperature or extremely low temperature, depending on the reactions that are needed to produce your ADOX. ADOX are actually the raw materials needed in the production of any new compound. Now, it is an ester as a product of alcohol and acids. And the first generation of pyrethroids, as I have mentioned a while ago, they are highly unstable. They are quite sensitive to light, air, and temperature. Its production was mainly for the control of indoor pests like household pests such as cockroaches, flies, and other pests found indoors. Okay. The next generation pyrethroids came 15 years after, when the first generation insecticides was released in the market. And during this period, there were 5 pyrethroids that were produced with improved efficacy and improved efficacy of the previous pyrethroid produced. That one was alitrine. The tromethrine was produced first, then it was followed by resmetirin. This time, resmetirin is 20 times as effective as pyrethrum. Then we have another product that is even more active compared with resmetirin. This is more effective than pyrethrum, and then it was produced the same year as that with rismetrine, but now with improved efficacy and activity. The next second generation pyrethroid that came out in the market was bioallethrine, which was synthesized in 1969, and the last product that was produced in generating second group of insecticides is phenolphthalein in 1973. These second generation insecticides are still available, but they are already overtaken by the next generation insecticides in terms of efficacy, and they are not that effective. Although they are effective, but their efficacy and activity is less than with those produced later, those that are classified as third generation pyrethroids and the fourth generation pyrethroids. Now, the pyrethroids produced during this time, it was used worldwide for agricultural pests, and their use became popular since pyrethroids are less toxic to people or other mammals, and they are more toxic to the insecticides. The second generation pyrethroids, resveratrolene, rismetrine, and bioallethrine, we are going to examine how each of these differ from each other. So here, what is important, it contains the cyclopropane ring and then the ester part of the molecule. And the rest are just plain substitution, improving the efficacy of such pyrethroid insecticides. All of them share the same part of the molecule in this. So this one, what it only differs in this part of the molecule. Here you have actually heterocyclic rings attached to it. Now, the third generation pyrethroids, they are more stable. Why? It would answer to one of each not so good properties, the weak properties this third generation, the second generation pyrethroids have. For the third generation pyrethroids, it also appear on almost the same time towards the last part of the production of the second generation pyrethroids. Here, the problem of instability was solved by incorporating halogen in the molecule, like here. No? Here, in the case of permethrin, you have there 2 units of chlorine attached to this double bond carbon, and for phenvalerate, both shared the same part of the molecule here, but varies already in this part. Now here you have a ring that is chlorinated, and plus the addition of cyanom moiety, making it more active than permethrin and more persistent than this one. Now with this structure here, we can also further classify this into type 1 and type 2, which I will be discussed later in the course of our discussion. For third generation pyrethroids, these are the insecticides that are considered of exceptional insecticidal activity and photostability by changing some of the structures of the older pyrethroids. The difference here, as I've said, is the presence of halogen plus the toxic cyanofunctional moiety. Okay. For the fourth generation, pyrethroids are the one you can buy in the market. You can have as many of them. I will just show you because it's not the actual figure here. Okay. Then you can have this kind of you can have this kind of insecticides comprising bifenthrin, lambda-cyhalothrin, cyflothrin, deltamethrin, and so on and so forth. And the recent one is imidazothin. Now, this is actually a sort of a combination of two active ingredients, the neonicotinoids from imidacloprid and then from the permethrin. This time, some manufacturers already produced formulation containing two or more active ingredients to increase its efficacy rate and the spectrum of the insects that will be targeted. The fourth generation pyrethroids are more effective than the third generations, and these pyrethroids are photostable. They will not undergo photolysis or splitting of the molecules upon exposure to sunlight. And they are more stable. They can have efficacy up to 10 days after application under optimum condition. So some of these fourth generation pyrethroids which you can buy in the market, the bifenthrin, the tamethrin, lambda-cyhalothrin, and cyflothrin, but you have even more and more of this. Now, the fourth generation pyrethroids are mainly used to control agricultural pests, and it is a group of insecticides that offer most resistance to exposure to sunlight and air. And in this manner, they are considered more or less persistent. While synergists are added to pyrethroids, especially in the second to third generation. We know that synergists are one of the components in a pesticide formulation. In the case of pyrethroids, it's no longer needed for the fourth generation insecticides. You only need this synergist to increase efficacy in second and third generation insecticides. Synergists, by the way, are compounds. If you could still remember what synergists are, these are compounds that are non-toxic by themselves when they are not used to begin with, but then once they are incorporated in another compound, the the efficacy, the activity of the other compound is enhanced by its presence. And for pyrethroid group of insecticides, it can even increase up to 10 to 20 times more effective than without synergist added to these insecticides. Okay. Now, I mentioned a while ago that the different group of insecticides, especially in the third generation and fourth generation insecticides, these insecticides can be further subdivided into two groups according to the chemical structures and to and to the and also on the presence of the cyano group in the molecule. We have here type 1 and type 2. How these two types of pyrethroids differ from each other. Then for type 1, you have no cyano moiety at the alpha position, where this cyano part of the molecule is found. Then in type 1, it would maintain its basic cyclopropane carboxylic esters. In contrast with type 2, it has already has the cyano moiety at the alpha position, and this part of the molecule would give better insecticidal activity, photostability, and the potential for greater mammalian has the characteristics, it is not the one that we are looking for, but anything we add on the materials, it could either increase its potency or decrease its potency. If there is a, in this case, the insecticidal activity is being enhanced, but in the same manner, the mammalian toxicity is also further increased. Now, what are these insecticides where this type 1 and type 2 insecticides belong? For the type 1, where there is no cyanomoiety present in the molecule, we have the alethrin. This is the first generation insecticide. Then we have permethrin, bifenthrin, and deltamethrin. You have also other insecticides not mentioned here. As long as in the molecule you cannot see the cyano functional moiety, then it belongs to type 1. For type 2, we have the cypermethrin, phenvalorate, and cyclotrin, and the lambda cyhalothrin. And in terms of its characteristic in as insecticidal compound, type 1 has the ability to knock down the insects quickly. In contrast with type 2, here it will not possess knockdown effect, but it can induce higher insect mortality. Here, the mortality would be fewer compared with type 2, since the knockdown insects have the ability to recover, especially if the amount of insecticides they are exposed to are just at the sublethal dose. Okay. Now, how about the mode of action? Pyrethroids is also considered as a nerve poison, but not as potent compared with that of carbamates and organophosphorus insecticides. For the organophosphorus and carbamate insecticides, what is being acted there is the acetylcholinesterase, the enzyme. It is more of chemical aspect, the reactions that would take place. In this case, for pyrethroids, it's on the physical action, where the voltage-gated sodium channels are affected. And sodium channel is a membrane protein in the axon of the nerve cell with a hydrophilic interior. The interior is shaped precisely to allow sodium ions to pass through the membrane, enter the axon, and propagate an action potential. And if this would happen, when the channels are left in the open state, the nerves cannot repolarize. Repolarization is very important. It is a state where we have, it's a so-called like a resting stage of the activity. In this case, when there is no repolarization that would take place, it leaves the axonal membrane permanently depolarized, and at this condition, it would result to paralysis of the organism. This is almost the same as that of the chlorinated hydrocarbons, wherein the nerve, the voltage-gated channels are affected. Another feature wherein we have to look at in pyrethroids. Normally, pyrethroids, especially the second or third generation pyrethroids, synergies are no longer necessary. I mean, they're still necessary, but for the fourth generation, it's no longer necessary. The action of synergies like piperonal butoxide is, it would inhibit now the key microsomal cytochrome P450 enzymes in metabolizing the pyrethroid. no presence of uh, mic, micros P450 as an enzyme, then these pyrethroids would be kept in its original state, and it keeps on targeting the target site that is now the voltage gated channel and affecting the normal activity in this part of the nervous system. Now, for new generation pyrethroids, application of synergist will not significantly increase the efficacy of our pyrethroids. Using synergists would even become costlier since the added advantage it can give to pyrethroids is not that much. So for new type of pyrethroids, this is no longer needed actually. Okay, so much for the lecture for today. We have 30 minutes left before the end of our classes, and we will use this time discussing what you have learned from the 40 minutes lecture I gave you, and also asking you something, some questions, or letting you summarize what we have achieved in our 40 minutes lecture on pyrethroids. And you have to take notes since these are the most likely questions that would appear in the final exam. Okay, now our lecture is over, but I have to wait your questions, or if I miss something which you want to learn more. I cannot give the very details of which it will be given in the advanced toxicology class. What is important as undergraduates is to know the different kinds of insecticides, what are these insecticides in each group, how do these insecticides appear structurally in terms of chemistry, why they are that toxic, why and where are their site of actions and the mode of actions as well. Anybody? Can I call May? May, are you there? Can you summarize of the 40 minutes discussion we have? May? Wala. Jennifer did a good job in summarizing in terms of carbamates, but this time I need somebody else that can summarize the lecture we have on pyrethroids. Jen can entice others to be more participative in sa manaadiri. Jose Roland is also participative in our previous lectures. This time maybe there's a problem in connectivity. I know he is so participative and asking questions, especially if he wants to be more clarified with the discussion. Jared also participated. How about Dave? Dave, are you there? Or anybody that can volunteer? Anybody? Wala? I don't know if you understand my lecture. I'm not comfortable enough letting the lecture.
Then, ma'am,
Yeah, May? Go on,
I have
May.
question, ma'am.
Can you summarize the topic on pyrethroids? What you have learned in the 40 minutes discussion?
Pyrethroids, ma'am, kay it is an insecticides, ma'am, kanang came from a flower, ma'am ba?
Mm-mm.
Ako nakuha
The
then
basis,
kuha na
no?
siya, ma'am, kanang belongs to kanang mga chrysanthemum, ma'am,
Mm-hmm.
na
Very good.
kanang
What else, May?
nya. It has a highest concentration, ma'am, of
Mhm.
insecticidal metabolite, pyrethrin.
Yeah. Anything else? Maybe we
Mm.
can ask the others to follow. No, you started it right, or you can add more if you want. As a Sherilyn, maybe Sherilyn can add more of have what May gave a while ago or discussed. Sherilyn, are you there? Wala. Maybe,
Yes, ma'am.
oh, sige, Sherilyn. Good. You will
Kuan.
actually will be assessed on your participation too.
Um, in addition to what May said, it
Uh-huh.
contains, in addition to what May said, it contains six variable mixtures of esters,
Uh-huh.
which are susceptible to light, moisture,
Mm-hmm.
air. Then it possesses a knockdown properties, and
Uh-huh.
unstable compounds, and non-persistent.
Okay,
That's
very
all.
good, no? How about the others? In terms of mode of action, then we will call the other students. Or if you want to finish it, May, do you want to add more? Or we will reserve it for the other students? Si Edward is also very participative, actually. I don't know his connectivity since I saw him that is disconnected every now and then. I don't know this time. Wala, wala siguro kay wala man ng response si Edward. Si Jedex or si Jonaline. Jonaline?
Ma'am.
Jeneline, can you also add more, especially on the mode of action of pyrethroids?
Okay. So the mode of action resembles the mode of action also of DDT. It is considered as axonic poison, and
Uh-huh.
when the toxin are kept in the open state, in the channels in the open state, there is no the nerves cannot repolarize again.
Uh-huh.
Then in the case of the grouping, it is divided into I in the grouping, there are four generations. The first
Mm-hmm.
generation, which is the Alice ring, then the second generation, which includes the tetramethrin,
Mm-hmm.
resmethrin, bioalethrin, and bioresmethrin. The third
Mm-hmm.
generation, which includes the phenvalurate and permethrin.
Mm-hmm.
Then the fourth generation, which includes the bifenthrin. Isara ako na dumduman mo.
But you have discussed a lot. I'm so happy that you're able to capture the important aspects. And I'm so happy that there are a number of you who participated, meaning to say you really listened to my lecture and try to put it in a summary, and for sure you will answer one of my questions. Thank you, Jeneline. Thank you, May. Thank you, Sherilyn. Thank you, Jared. And thank you, who else? Jennifer. But I also saw others who participated in our discussion. And for those I failed to mention, you know who I cannot remember all as we go along, because especially in the carbamates part. For today, we're done with two lectures that is on carbamates and pyrethroids. And I hope you learned a lot from our almost 2 hours discussion. You are now equipped if somebody would ask you which kind of insecticides we're going to recommend for a particular pest. And for this, you have already an idea of these different insecticides, what they are for, why they are more questions, at least somehow you will have something to share to those who want to ask, especially in terms of pesticides. Okay? Do you want to ask more things you want to learn, which I did not include, since those information would be given in the higher toxicology course if you want to pursue your graduate degree. Then it will be one of the courses that will be offered, especially if you will take MS in entomology or MS in plant protection. Okay, I'm happy that many still remains with this period. Um, when I did the lecture in 10:30 until 12:30, many left. Maybe they were already hungry. Not the lecture went for 2 hours, and we ended up at 12:40. And I was so considerate, and I understand that they were already hungry at lunchtime, and they have to take their lunch. And there was also a problem of connectivity at that period. And if you don't have questions anymore, we are 20 minutes earlier to finish the 2 lessons. And I assume that you don't have questions anymore, but then I can still entertain questions for another 19 minutes if you have more, and I'm ready to answer those queries of yours with the time left. Napa, especially those who did not participate in our discussion, it's time now that you can ask to me rather than me asking you to answer those questions. You can ask more if you want. Si Rhea, do you have questions, Rhea? Or si Carol? Rhea, do you have questions, Ray?
Wala na, ma'am.
Clearly understood?
Yes,
Okay
ma'am.
na? Especially the ones mentioned by your 6 classmates, no? In pyrethroids. Na, how about Pamela? Pamela?
Ma'am, nag-chat, ma'am.
Okay, nakag-chat. Okay, good.
Sila.
Tanan ba nga 6 pyrethroids kay stable? What do you mean sa 6 kadto sa naturally occurring? Asa man ato, Jen? Which of those, Jen? Kay katong 6 siguro, katong synthesis of 3 alcohols and 2 acids. Ato ba to, Jen? Is it the one? Asa man ato? By the way, all of these 6 pyrethroids, if you are referring to the ones produced in the synthesis of 3 alcohols and 2 acids, they are unstable. The instability of these compounds became the basis of producing the newer generation insecticides after the production of the first generation. Then in its generation, there are lots of improvement done until the 4th generation, wherein you have already more stable pyrethroids produced by incorporating halogens in the molecule. But for pyrethroids that don't have halogens in it, and if they are just simple type of molecule, then they are considered as unstable. So the six pyrothroids, maybe I can say, if you are referring to the synthesis of three alcohols and two acids coming up with six esters, they are all unstable. No? They are photolabile. They are easily degraded after exposure to moisture and air. Jennifer, I will just type here. And I answer
One is for
questions.
unstable ka, ma'am.
Huh? Did I answer your questions, Jen? If you're referring sa katong synthesis of three alcohols and two acids, then they're all unstable. The third generation and the fourth generation, these are the pyrethroids that are more stable. There are a lot of adjustments done in the molecule. Okay. So, how about the others? Thank you, Jen. You're so participative. Let me see for the others. See Carol. Carol, are you still there? Can you hear me?
Yes, ma'am.
What can you say? Or do you have some questions that are not included?
Wala na, ma'am.
Wala
Clear
na?
man, ma'am.
Okay. So do you agree with those discussed by your classmates before? You agree with their answers?
Yes, ma'am.
Okay, good. Now I'm very happy that all of you stay until the end of the lecture. It is indicative that you are somehow interested to listen in this 2 hour period, and the 1 to 3 period is not a good one. It is considered a unholy hour. We tend to be sleepy, especially this time that I don't have control. We are not in a face-to-face learning system, and my only control here that you are around, that I can still see you, that you are still in our class. Okay. Okay. Since you don't have questions anymore, I will declare this lecture of ours ended, and I hope you have a more productive afternoon left after our discussion, and stay safe. Stay that you don't get infected with COVID or other illnesses. I wish you all the best of health. That is very important to us, and we can finish our discussion with no mga sabit. Yeah. So thank you so much, my dear students, for being there. And we only have 2 more meetings left, and we will finish our discussion in these 2 meetings. And I think we still have, after the last meeting, the remaining 4 lectures are not that much compared with the 4 lectures we have just finished. Then I can give more time on the last week before the final exam will be given. You will be guided on what kind of probable questions that would come out in the exam. I don't know the grade you have in the first half. I have not seen it yet. And I know that many of you were doing well, actually. Based on our discussion, I can already sense who are those really doing well in the exam. Okay, thank you so much, my dear students. Have a nice afternoon again.
Thank you, ma'am.
Bye-bye.
Thank you,
Bye-bye.
ma'am.
You're welcome.
Thank you,
Bye-bye.
ma'am. Thank you.
You're welcome.
Ay, kemana yan?